Okay, so welcome to the week 2 notes. I'm just going to kind of quickly give you an overview of the notes, then I will start on the first section. This section is all about the revision of the really basic material of what you covered in Business Stats 2. Now, this is really the emphasis of this class is on practical data analysis of larger data sets. But the hypotheses tests that we actually cover in this class are actually used within some of the bigger kind of techniques that we're implementing. So they are pretty important. If you don't know what a hypothesis is or what a p-value is, you're not going to be able to understand, some of the more advanced techniques that we cover in this class. So having said that, this week, I'm going to split it into multiple videos. The first, we're just going to go over the idea of sampling. And we're also going to talk about, why we use the normal distribution, why we keep, when you're in your stats class, you're in a bit crazy drawing all these bell-shaped curves. We will then move on to single sample hypothesis test, single sample confidence interval, two sample confidence intervals, then exactly the same for hypothesis tests. So again, this is just the stuff that you did in your business stats. I'll review it briefly, and then we'll show you how to implement things in R. Now, a few notes about this week. I've included lots of kind of links in the notes. So I've included links to material. So again, you had the little revision quiz last week. You also have hopefully a cheap old business stats textbook that I recommended for this class. And I give you a few additional links. Okay, having said that, why do we do these sort of tests? So let me get a new canvas to work with. And let's just say that we won't bother with a sampling frame at the moment. We'll just kind of keep it simple. Let's just say that we have a population. And this is the population of all female consumers. This is like everybody aged above 18, female in the US, which is probably about 320 over 260 million, minus kids, probably about maybe, let's just say this is 130 million people. And we want to know some information. We want to know, let's get rid of that bilious color. We want to know the mean fashion spend. And apologies, this pad makes my bad writing even worse. But that's the mean fashion spend of these consumers. Maybe it's like we're trying to work out, the market potential for a new, maybe fast casual online website. So we want to know the mean fashion spend. Now, we can't go out and sample all 130 million consumers. So we kind of take a sample of maybe 10,000 consumers. So we take a random, and the key word here, if we're doing statistics, is we need a random sample of consumers. And let's just say we have n equals 1,000 consumers. Now, in that random sample, we calculate the X bar, and that's the mean fashion spend within the sample. And all statistics is we're really making an inference. We're trying to find information about this guy using this guy. So we're making inference on the population using the sample. Whether it's using a confidence interval or a hypothesis test. That's all we're doing. And sometimes we're making inference on, let me get my black pen back. This is the amount of variation in the data. with this as the standard deviation. And that's just kind of how spread out the data are. I'm not going to I'm sure you've seen the formulas before. I'll refer you back to your stats textbook. Okay, and again, in the sample, we have S squared, which is the sample variance. And we also have the sample standard deviation. So what's all this stuff regarding all these normal curves? Why do we keep drawing normal curves like this? Well, imagine that I take a sample of maybe 50 consumers. So I take, for my previous example, I take 50 consumers. So we say n equals 50. I take another sample of another 50 consumers. And I take another sample of 50 consumers. And then I plot, I calculate for each of these, I calculate the mean, the sample mean. So I calculate the x bar for each of these. Then if I'm to plot all these graphs, if I'm to plot all these x bars, then I actually, and I do like a histogram and draw a curve all over it. Oh, that should be bigger, sorry. Sorry, that was a terrible attempt at drawing a distribution. This is why I use R. So what we have here is we have this kind of what should be a normal distribution, what should be symmetric if I could draw properly. So we have what's called a sampling distribution. And the idea is this is normal. Sorry. This is normal, which means it's basically bell-shaped. And important, it has a standard deviation, a kind of a standard deviation. We sometimes call this the standard error. Which is going to be sigma all over root n. So this is, each of these maybe has a variance sigma, and the overall population has a variance sigma. So the population variance is sigma. And the sampling distribution has sigma over root n. And generally we don't know this, so we just kind of estimate using the sampling standard deviation. So, relatively simple. We take all these samples of n equals 50, we put them in this sampling distribution, and our kind of target distribution is normal bell-shaped, and it has a standard deviation of s over root n. And just think about it, you know, just the intuition here. This basically means as n gets bigger, the distribution of this actually gets kind of thinner as my standard deviation goes down as my n gets higher. And this makes a lot of sense. So imagine I was grabbing people, I was trying to work out the average calories consumed by a Mississippi State student. And imagine if I took samples of n equals 2. Then I might well get 2 football linemen. And I might get, you know, average calories per day of 7,500. But I also might get 2 people on the diet, so I might get 2,000. But if I took, say, n equals 50, it's unlikely I'm going to get 50 football linemen. So my numbers are going to be much closer to the overall population mean. So as the sample size goes up, the variance of the sample actually goes down. The variance of the sampling distribution. Okay, so let's just like demonstrate this now in R. And this is in the notes, but I'll kind of go through it from the code. And we're loading in some information. So again, just as a reminder, each of my week codes, just put them in whatever your working directory is. Mine's BQA Analytics. And this is actually some real data. This is from the Yelp website. I'm sure you've heard of that. It's an online review website. And gathering the data, I actually managed to get kicked off the Yelp website for my data gathering activities. And what it is it's a lot of different restaurants in the Milwaukee area and Chicago. I think it's Chicago in as well. And it's the number of reviews. So this is basically a load of restaurants, how many reviews are in the restaurants. Now, you're going to get basically, and this is of restaurants that have at least one review. It'd even be more skewed if we had those with zeros. But basically, you get a lot of suburban mom and pop restaurants with maybe have 1 or 2 reviews, an Applebee's or something. And then you get some really trendy downtown restaurants that literally have hundreds of reviews. So this distribution is not very even. So what do we do? Let's just plot this distribution. First, we'll calculate the mean. So the important function here is mean. This just calculates the mean of any vector of data. So mval is the mean of the review counts, and that's 14.24. And we also have the standard deviation. And that's 33. And what we're going to do is we're going to draw a histogram. And we played around with histograms last class. I'm a bit fancier here. So let's just I'll tell you what this code means. So I'm doing the histogram of these review counts. Main, this actually just tells us this is my title. And I actually put the mean and the standard deviation in the histogram. And basically what I use is I use a function called paste, and it allows me to paste different pieces of text together. So I have my main, hist of review counts mean equals. Then I actually, there we go, sorry. My computer's a little bit slow today for some reason. It allows me to, where were we? Change a number into a string. So this is what format does. And then we have SD, and that's basically, again, the same for the standard deviation. We also have the review counts, and as the X label, it's the number of review counts, and then a little bit on the colors. And I set, as remember I told you last week, I set the number of breaks and the fact this is the probability histogram. Now what we do is the denorm function actually produces a normal curve. And so what we're doing is we're actually going to use the denorm function, and that is going to basically draw a red normal curve on top of my distribution. So denorm will actually give you the values for the normal distribution if you supply it the x's, and LWD tells me how thick it should be, and add just means I add it to the existing histogram. Okay, so let's do this. Let's draw our histogram. So here's my histogram here, and you can see, whoa, this guy's really skewed. You've got all these mom and pop restaurants, and then you've got like a few like trendy hipster restaurants up here. Now let's draw a curve on this. It's not going to be very successful because it's definitely not a normal distribution. And you can see the curve is like a long way away from being like a normal distribution. Okay, now what am I doing now? Well, I'm going to take samples of size 2. So I'm literally going to take 2 restaurants, calculate the mean. Take 2 restaurants, calculate the mean. So let's just have a look at this little bit of code. What does this guy do? All that does, the sample basically says I'm going to take 2 of these restaurants randomly and I'm going to calculate the reviews. So basically just takes 2 numbers, divides them by 2, divides them by 2. And then I do this 1,000 times, so I now have 1,000 sample means. The for loop, this is just standard programming knowledge, goes for I in, and I doesn't mean anything, it's just what we call an iterator. It just tells you the number of the loop. So for each number of the loop in 1 to 1,000, we literally do this 1,000 times, and I goes 1, 2, 3, 4, all the way up to 1,000. And we create a vector called mean sample, which at the beginning is just a load of zeros, and then we fill in all these sample means. So let's do this. Mean sample I is the actual the mean of the two restaurants we randomly picked. We do it 1,000 times. Now let's look at mean sample, and there we go. We have our 1,000 samples of 2. Now we do exactly the same as before. We calculate the mean standard deviation, draw a histogram and draw a curve on it. Remember last time we had a mean of 14, standard deviation of 33.5. Now, look here. We've still got a similar mean, but our standard deviation has dropped. Plus, this graph is now not quite as extreme. You see, we're not quite a normal curve, but we're getting a little tiny bit closer to it. Now see what happens with a sample of size 100. So I won't go through it again, I've gone through it, doing exactly the same, but we're taking samples of 100. Basically 100 reviews, calculate the mean, 100 reviews, calculate the mean. And now, aha, it almost looks like a normal distribution. So this is what we're relying on. And generally, if n is over maybe 50 is the usual, or sometimes 30, we take the samples, then the distribution of the sample means is relatively normal. That's just all these curves that you kind of draw in class. So let's just kind of summarize this little video. And this, we're not going to prove it mathematically in this class because this is not the right class for too much math. And we'll say we have random samples of n. Let's just be n is greater than or equal to 50. And let's just draw this. The distribution of sample means. Oh God, that's such a poor attempt at a normal distribution. I apologize. Yeah. Let's just try again. That's a little bit better. Anyway, so we'll say of this distribution, the expected value of this distribution is basically the mean of all of these x bars. And that's basically say, it's the average of all of the means. Don't worry too much about the notation. And it has a standard error of sigma over root n. So basically all you need to know is it then gets bigger, it gets narrower. Kind of common sense. And then next video we'll go on how to use this practically.